It is true that the advent of digital relays has changed the landscape of current transformer, or CT, applications. Digital relays are capable of handling both measurement and protection functions using a single CT, often eliminating the need for separate dedicated CT. The National Electrical Code, or NEC, doesn't explicitly mandate separate CT for measurement and protection. However, it offers guidelines that indirectly address this concept. ANSI Section 215.12 states that current transformers should be used for metering only where the sum of the burdens of the connected metering devices does not exceed 50% of the current transformer's rated burden. This statement implies that if the burden imposed by protection devices passes 50% of the CT capacity, employing a separate CT for protection purposes becomes advisable. It's worth noting that digital relays generally have significantly lower burden requirements, alleviating this concern in many scenarios. Now let's delve into the ANSI standard. ANSI C37.90 1-2012, titled Standard for Relays and Relay Systems Associated with Electric Power Apparatus, offers comprehensive guidance on using CT for measurement and protection. Section 15.1.2.1 explicitly states that current transformers may be employed for both metering and protection purposes. However, it emphasizes that the protection function shall not be compromised by the metering operations. This underscores the importance of ensuring that protection functionalities remain unhindered when a single CT handles both measurement and protection tasks. In conclusion, while the NEC doesn't explicitly dictate separate CT for measurement and protection, its guidelines suggest considering separate CT if the protection burden exceeds 50% of the CT rated capacity. The low burden characteristics of digital relays often make separate CT unnecessary. ANSI C37.90 1-2012 further elaborates on using CT for measurement and protection, highlighting the critical aspect of maintaining unimpaired protection functions. Let's delve deeper into the technical aspects. A current transformer, or CT, is a type of transformer that is used to measure alternating current, or AC. It produces a current in its secondary which is proportional to the current in its primary. Current transformers are used to measure high currents that would be too difficult or dangerous to measure directly. They are also used to isolate the measuring instrument from the high voltage of the primary circuit. The core of a current transformer is typically made of laminated steel. The primary winding is typically a single turn of heavy gauge wire, while the secondary winding has many turns of smaller gauge wire. The turns ratio of the transformer determines the ratio of the primary current to the secondary current. For example, a CT with a turns ratio of 100:1 will produce a secondary current of 1 amp for every 100 amps of primary current. Current transformers are used in a variety of applications, including power metering, protection, and control. They are an essential part of any electrical system that uses high currents. When selecting a current transformer, it is important to consider the following factors. Firstly, the primary current rating. Secondly, the secondary current rating. Thirdly, the accuracy class. And fourthly, the burden rating. The primary current rating is the maximum current that the CT can safely measure. The secondary current rating is the current that the CT will produce in its secondary winding when the primary current is at its rated value. The accuracy class is a measure of the CT accuracy. The burden rating is the maximum impedance that can be connected to the CT secondary winding without affecting its accuracy. The burden is the load, expressed in volt-amps, imposed on the current transformer secondary. It represents the impedance of the metering and protection devices connected to the CT. A higher burden means a greater load on the CT. Digital relays, due to their electronic design, typically present a very low burden compared to older electromechanical relays. This is a key reason why a single CT can often serve both metering and protection functions when used with digital relays. The NEC guidelines, particularly Section 215.12a, are in place to ensure the CT accuracy is not compromised. If the total burden exceeds 50% of the CT rated burden, the CT accuracy can be negatively affected, leading to inaccurate measurements and potentially unreliable protection. In such cases, separate CT for metering and protection are recommended to ensure both functions operate optimally. ANSI C37.91 provides more detailed guidance, especially concerning the interaction between metering and protection functions. It emphasizes that the protection system must not be impaired by the metering system when using a single CT for both. This means the CT must be selected and applied in such a way that the metering functions do not introduce errors or delays in the protection system's response. For example, the CT should be sized appropriately to handle the full range of fault currents without saturating, which could degrade the accuracy of both metering and protection. When designing a system with CT, engineers must carefully consider the specific requirements of both the metering and protection systems. They need to calculate the total burden imposed by all connected devices and ensure that it remains within the CT rated burden. They also need to select a CT with an appropriate accuracy class for the application. For metering, a higher accuracy class is generally required. For protection, the CT must be able to accurately reproduce fault currents under a variety of conditions. In modern electrical systems, digital relays offer many advantages over older electromechanical relays. They are more accurate, more reliable, and more flexible. They also have lower burden requirements, which makes it possible to use a single CT for both metering and protection in many cases. However, it is still important to carefully consider the specific requirements of each application and to select CT that are appropriate for the task. Let's discuss some specific scenarios where separate CT might still be preferred. Firstly, in critical protection applications, where the reliability of the protection system is paramount, separate CT may be used to provide redundancy. This ensures that the protection system will continue to function even if one CT fails. Secondly, in applications where the metering and protection systems have very different accuracy requirements, separate CT may be used to optimize the performance of each system. Thirdly, in applications where the burden imposed by the metering and protection systems is very high, separate CT may be used to reduce the overall burden on each CT. Choice between single and dual CT also depends on the type of protection being implemented. For example, differential protection schemes, which compare currents at different points in a circuit to detect faults, often require dedicated CT with specific characteristics to ensure proper operation. Similarly, high-impedance fault detection schemes may also benefit from separate CT to minimize the impact of metering burdens on the fault detection sensitivity. Furthermore, the physical layout of the electrical system can influence the decision. If the metering and protection devices are located far apart, it may be more practical to use separate CT to minimize wiring costs and reduce the risk of interference. In summary, while digital relays have made it possible to use a single CT for both metering and protection in many applications, there are still situations where separate CT are preferred. Engineers must carefully consider the specific requirements of each application and select CT that are appropriate for the task. They must also be aware of the relevant NEC and ANSI standards and guidelines. Now let's talk about CT saturation. CT saturation occurs when the magnetic core of the CT can no longer linearly translate the primary current to the secondary current. This happens when the primary current is very high, such as during a fault. When a CT saturates, its accuracy is significantly reduced, and it may no longer be able to provide reliable measurements for metering or protection purposes. To prevent CT saturation, it is important to select a CT with an appropriate knee point voltage. The knee point voltage is the voltage at which the CT starts to saturate. The knee point voltage should be high enough to ensure that the CT will not saturate under the highest fault current conditions. There are several methods for calculating the required knee point voltage. One common method is to use the following formula: knee point voltage equals K times CT ratio times RF plus RL, where K is a constant that depends on the application. CT ratio is the turns ratio of the CT, RF is the fault resistance, and RL is the lead resistance. The fault resistance is the resistance of the fault path. The lead resistance is the resistance of the wires connecting the CT to the relay or meter. Another important consideration is the CT secondary winding resistance. A higher secondary winding resistance can contribute to CT saturation, especially under high fault current conditions. Therefore, it is important to select a CT with a low secondary winding resistance. In addition to selecting an appropriate CT, it is also important to properly install and maintain the CT. CT should be installed in a location where they are protected from damage and contamination. They should also be regularly inspected to ensure that they are in good condition. The connections to the CT should be tight and clean to prevent voltage drops. The CT burden should also be checked periodically to ensure that it is within the CT rated burden. It is also important to ensure that the CT is properly grounded. Grounding helps to protect the CT from damage due to overvoltages and also helps to improve the accuracy of the CT measurements. Current transformers should be tested regularly to ensure that they are operating properly. Testing can be performed using a CT analyzer. A CT analyzer can measure the CT turns ratio, accuracy, and burden. It can also detect CT saturation. The results of the CT testing should be compared to the CT specifications to ensure that it is operating within its rated limits. If the CT is found to be faulty, it should be replaced immediately. Failing to address a faulty CT can lead to inaccurate measurements, unreliable protection, and potentially dangerous situations. In summary, selecting, installing, and maintaining CT requires careful attention to detail. Factors such as burden, accuracy class, knee point voltage, secondary winding resistance, and grounding must be considered. Regular testing and inspection are essential to ensure that CT operate reliably and accurately throughout their service life. Another area worth discussing is the impact of harmonics on CT performance. Harmonics are unwanted frequencies that can distort the sinusoidal waveform of the AC current. These harmonics can be generated by various nonlinear loads, such as variable frequency drives, or VFDs, and electronic power supplies. Harmonics can have a significant impact on CT performance, particularly in metering applications. They can cause the CT to produce inaccurate measurements, leading to errors in billing and energy management. In protection applications, harmonics can cause the CT to operate incorrectly, potentially leading to false trips or failures to trip where fault occurs. To mitigate the effects of harmonics, it is important to select CT that are designed to operate accurately under harmonic conditions. These CT typically have a wider bandwidth and a higher accuracy class. It is also important to use filters to reduce the harmonic content of the current. Filters can be installed at the source of the harmonics or at the CT location. In some cases, it may be necessary to use special CT that are specifically designed to measure harmonic currents. These CT are typically used in applications where it is important to accurately measure the harmonic content of the current for monitoring or control purposes. The choice of CT also depends on the specific application. For example, in revenue metering applications, it is important to use CT that meet the requirements of the relevant metering standards. These standards specify the accuracy class, burden rating, and other performance characteristics of the CT. In protection applications, it is important to use CT that meet the requirements of the relevant protection standards. These standards specify the CT ability to accurately reproduce fault currents under a variety of conditions. When selecting CT for use in hazardous locations, it is important to use CT that are certified for use in those locations. These CT are designed to prevent explosions and other hazards. It is also important to follow all applicable safety regulations when installing and maintaining CT in hazardous locations. In addition to the technical considerations discussed above, it is also important to consider the cost of the CT. CT can range in price from a few dollars to several $1,000s. The cost of the CT will depend on the size, accuracy, and features of the CT. It is important to select CT that are appropriate for the application and that meet the budget requirements. When purchasing CT, it is important to purchase them from a reputable supplier. A reputable supplier will be able to provide you with CT that meet the relevant standards and that are backed by a warranty. They will also be able to provide you with technical support and assistance. In conclusion, selecting, installing, and maintaining CT is a complex process that requires careful attention to detail. By following the guidelines discussed above, you can ensure that your CT operate reliably and accurately throughout their service life.